Hello, welcome back to Learn It from a Layman. I am Carl Christensen, and I am solo podcasting for the first time. So, this will be a new experience for everyone involved, meaning me and you. And so, hopefully, this goes well. I've done some preparation today for today's subject, which is astronomy. I guess we could call it. We've got a whole Basics of Science series. So, this one's, I guess, Basics of Astronomy. We've done um, a kind of astronomy-based podcast in the past with 10 interesting things about space. If you want to go back and listen to that, that's more let's call it eclectic. This one's more just the some of the basics, a few of the interesting facts about our galaxy, and some of the things you might learn in a beginning astronomy class. So let's start with the sun. Um, our sun is about average sized and about middle-aged. So nothing particularly extraordinary about our sun, except that it's ours. Uh, it is classified as a yellow dwarf. It is on the large side of a yellow dwarf star, so like I said, more average size than what a dwarf would lead you to believe. Um, but yeah, it's 4.3 billion years old. As far as suns go, that or stars go, that's set about middle age. It'll probably last. The scientists believe somewhere around another 7 billion years. So we're not in any danger at this moment. At 7 billion years old, it'll go. After another 7 billion years, it'll go to a red giant, which means it'll expand in size significantly, and then eventually end up as a white dwarf, which means it'll shrink substantially and kind of burn out slowly over the course of another multiple billions of years. Um, yeah, so if you're familiar with stars and how stars usually die, some large stars die as a supernova. Our sun will not go that route. It's not big enough. You have to be a very large star to go supernova. Uh, but in case you were confused about sizes of stars and uncertain about how big the sun actually is, let's put it into perspective. Um, the radius of the sun, and so if you're familiar with the radius, that's from the center to the outside of the star, um, is 864,938 miles, give or take. Um, so that, and for those outside the United States, convert that to kilometers. I get that that's a better measurement, but look, I'm American. I have to deal with what I've got to deal with. So, uh, a perspective for that large number, which is kind of hard to conceptualize. Essentially, the diameter of the sun is 109 Earths. So you could stack 109 Earths next to each other across the diameter of the sun. So it's incredibly large from the perspective of what we're used to. Like I said, not big in stellar perspective, but as far as what we deal with on a day-to-day, it's incredibly large. There are one of the large stars that you may have heard of before, Betelgeuse, is 700 times bigger than the sun. So that's obviously super massive. And that one, Betelgeuse, which you can see in the night sky, will probably go supernova soonish. And once again, soonish in the galactic perspective, and the probably sometime the next couple 100,000 years. Astronomers have started seeing some dimming in that star. They're not sure when exactly that's going to go supernova, but sometime. Probably not in your lifetime or mine. Um, all right, so that's a little bit about our sun. Let's talk a little bit about the Earth now. So we are, as we know colloquially, the third rock from the sun. I mean, there are two other planets closer to the sun, and those are Mercury and Venus. We are the only planet with that we know of, and certainly the only planet in our solar system with liquid water, which is pretty important, for life. So, pretty astounding planet we have that we live on. So let's be grateful for that. There are 8 planets in our solar system. As I said, I already mentioned Mercury and Venus. Those are rocky planets just like ours. Mars, also a rock planet. Um, and then we have the gaseous giants, which are um, Jupiter, Saturn, Uranus, Neptune, and those, which is, I took an astronomy class in college. I've done astronomy, kind of some small amount of astronomy throughout my life. I'm generally interested in the subject, but I wasn't even sure. I'd forgotten that. So when you think gaseous giant, these planets are supermassive. Most of them are gas. They do have a rocky core, though, and that's what I had forgotten. So there's rock in there. They aren't just a bunch of gas like, say, the sun. Um, all right, let's see here. As far as the size of planets, so Pluto, I'm sure you're familiar with the controversy over Pluto as to whether or not whether or not it's a planet. People my age, in their 30s, growing up, learned that there were 9 planets. Then it went back and forth for a while as there was some debate as to whether or not it should be classified as a planet. In case it's unclear, currently not classified as a planet. I don't think they're going to go back at this point. It is classified as a dwarf planet. And the matter of fact is that it's small. It's about 19% of the size of Earth. It's really distant, obviously. We already knew that, but there are at least 2 other objects, dwarf planets, that have been discovered that are of similar size to Pluto. So unless you want to say that there are probably 11 planets, then there's probably not 9, there's just 8. And besides that, there are a couple moons that are bigger than Pluto is. So, Pluto doesn't rank particularly high on the importance scale in our solar system. Maybe in your childhood, you had a soft spot for Pluto, but sorry. Um, yeah, so two other moons that are bigger than Pluto. Sorry, 2 other moons that are even bigger than Mercury. There are actually even more moons that are bigger than Pluto. But there are 2 moons that are bigger than Mercury. There's Ganymede, which is a Jupiter moon, and Titan, which is a moon of Saturn. Those are both even bigger than Mercury. Mercury obviously gets the planet status because it's closer to the sun, and it's a bigger percentage of the Earth's size as well. Um, Largest planet is Jupiter. Every planet except Mercury and Venus have at least 1 moon, and obviously in the case of Jupiter, Saturn, multiple moons, and actually a lot of the gas giants have multiple moons. Let's see. All right, let's talk a little bit about speed. So the Earth, lots of movement going on. We don't obviously feel it. Effects of gravity and atmosphere protect us from all that kind of stuff. But there are spins on its axis at about 1,000 miles an hour. So we're spinning like a top, as we obviously see the effects of every day. But it's also traveling around the sun, which once again we know as we change seasons, at around 67,000 miles per hour, or 30 kilometers per second. So once again, pretty good clip here. As you imagine the size of the sun, which we already discussed, and then the orbit of Earth around the sun, which is obviously we're quite a ways away from the sun, otherwise we'd all be dead, or we wouldn't even exist because there would be no atmosphere. So in order to make that trip around the sun in a year, then obviously we need to make some pretty good speed. The sun travels through space also, though, and this is something I think I learned in my college class for the first time, at least consciously. Maybe I had been told that before, but it isn't just us spinning and the Earth spinning and then also traveling around the sun. Our solar system is also moving. Additionally, our galaxy is moving, but the Earth. So essentially, the scientists have discovered or figured out that the sun is traveling through space at approximately 448,000 miles per hour, or 200 kilometers per second. So we are really whipping through the vastness of space at quite a speed. Um, so yeah, a lot of movement going on out there. Obviously, not a lot of resistance in space, not a lot of so we don't see the effects of that, and space being incredibly vast. We don't, like I said, we don't see those distances changing, but um, yeah, lots of movement going on. As far as the sun goes and our place in the galaxy, there are different arms. So we're in the Milky Way galaxy, which I believe most of us knew from grade school. Um, the Milky Way galaxy has multiple what we call arms, essentially clusters of stars that extend away from the center of the galaxy. And we are in, and they've been named throughout the years, we are in the Orion arm. And in the Orion arm, we're about a third of the distance out from the center. So the whole distance of that arm measured, we're about a third away from the center of the galaxy. So obviously on the outside of the galaxy, things are even whipping around faster. The center of the galaxy. Now this is fun. So if you are familiar at all with the night sky, which obviously if listening to an astronomy podcast, I'd imagine that you have some interest in the night sky. Maybe you know your constellations. If you've looked out before at the night sky, you've got Sagittarius, which is one of the recognizable constellations. Looks kind of like a teapot. That's what I always think of. And if you look above the spout of that teapot, that is you're then looking towards the center of the galaxy. Now, at the center of our galaxy, there is a supermassive black hole. It is 14.6 million miles in diameter, that black hole is. So once again, that is incredibly large. Once again, I have to put it into perspective. Our sun, as we already talked about, the radius of our sun is 864,000 miles in radius, so 14.6 million miles in diameter for that black hole. It's that supermassive. But it is, let's see, 26,000 light years away from us. So we're not in any imminent danger from the supermassive black hole, even if it were to eat the universe, which, as I was reading up about, it doesn't, not the universe, the galaxy, which at this moment doesn't appear to be doing much of that. Even then, the distance away from us it's irrelevant unless you're going to live for trillions of years, which not something we have to worry about. But so that's a little bit about the galaxy. Like I said, we have got all the stars in our night sky, at least all of the ones that deal with constellations, all the bright stars in our night sky, let's say. Those are all in our galaxy. Now there are things not in our galaxy that you can see with your naked eye, some nebula, some things outside the galaxy. Obviously, you can also visible with either binoculars or a pretty easy telescope, a pretty simple telescope. But as far as just looking up in the night sky and spotting constellations, those bright stars are stars that are close to us, obviously, and so those are ones that are inside of our galaxy. Now, thinking a little bit about the vastness of space, and talking a little bit about obviously the speeds that we travel through space, the size of these objects in space. Let's talk a little bit about distances between objects in space. So first, let's talk a little bit about the closest star. This is so there's an Alpha Centauri system that's approximately 4.3 light years away, and that star system has three stars. There's a star A and B, so Alpha Centauri, stars A and B, and then Proxima Centauri. Proxima Centauri is a little bit further away, still part of that system, but Proxima Centauri, Proxima obviously meaning close, so that is the closest star to Earth. I think just under around 4.2 light years. 4.2 light years. Now, in previous podcasts, we've talked a little bit about the speed of light. Light is a constant. Light and the speed of light in a vacuum is constant, right? C, and it's incredibly fast. We're talking 186,282 miles per second, or 299,792 kilometers per second. Once again, that's the speed of light in a vacuum. So, uh, I mean, it is inconceivably fast, right? And so, if you're talking about 4.2 years for light, that is the speed limit of the universe to travel from our star to the closest star, um, it's mind blowing, right? The distance of us to the closest star is well, it's more than can really be conceptualized unless you, I guess, deal frequently in galactic terms. Um, so let's now that we understand how close the closest star is, let's talk about the closest planet. So this is something that's been got a lot of press in the last, I don't know, 10, 15 years, where we've been able to figure out that there are actually a lot of planets out there, right? Lots and lots of stars have planets that orbit them. Um, and we've been able to find lots of planets in what they term the habitable zone, right? So that's a zone where the scientists believe that it's not too far away or too close to the star around which that planet orbits, or the Goldilocks zone also. So essentially where it's not too hot or too cold, and where there could conceivably be liquid water, and therefore habitable. Um, there are lots of other things to take into consideration besides, the zone that it's in, the state of the star around which they orbit matters. Well, lots of different things. Anyway, but the closest planet to us is actually, they've discovered that there is at least one, and I don't remember from my reading how many, but there is a planet that orbits Proxima Centauri, and that one, in some degree, looks a little bit promising, as far as it's in the right zone where it shouldn't be too hot or too cold. But there is some belief that it's very close to that planet is very close to its star. Proxima Centauri is a pretty small star, um, and so it orbits the star every 11 days. But because of its proximity to its star, uh, the orbit, the radiation might have pulled any atmosphere off, and so there might not be any liquid water. They're not able to tell at this point, um, as far as I know, at least. So there's still a lot of interest in that planet being only 4.2 light years away, and I say 4.2 light years away with a bit of a chuckle, because once again, that is significantly further than man has ever traveled. And we'll get to the end of this podcast and talk a little bit about what is conceivable for interstellar travel in the future. But yeah, that's the closest planet, and there are lots and lots. I said there are thousands and thousands of planets that have been discovered now, and that is groundbreaking for astronomy. So as of 20 years ago, 30 years ago, these things were conjectured but not necessarily discovered. And with the accuracy of our instruments now, and the technological advancements, we're able to confirm that these things exist based on all of these things we get from measurements of light, right? And then based on a spectrometer, we're able to figure out the wobble of a star. So essentially, when a star wobbles a little bit, there's a gravitational pull from something, and so we can figure out, okay, there's this planet, and we being here, I am classifying myself as an astronomer. I did have some interest in college about in becoming an astronomy major. I picked up the sheet that told me what I needed to study, and saw lots and lots of calculus, and I put that sheet back down and walked away. So I don't think I can classify myself that way. But anyway, the astronomers have been able to figure these things out, and I said it's been great to be able to figure out what is out there. Now let's talk a little bit about we've gone star and planet, closest star and closest planet. The closest galaxy to our Milky Way galaxy is the Canis Major dwarf galaxy. So not a large galaxy as far as galaxies go, but that once again, now we're talking intergalactic travel. That galaxy is 25,000 light years away. So, and that's the closest galaxy. So once again, the vastness of the universe is not to be understated. It's mind-blowing, and the distances even around our solar system to the next star, and then from stars in the same galaxy, and then from our galaxy to the next galaxy. I mean, these distances are just crazy. Like I said, and just so you, once again, you understand that the size of the galaxy, the distance across the diameter of the Milky Way galaxy is about 100,000 light years. Like I said, so our galaxy is pretty large, at least it sounds like it. However, the Andromeda galaxy is more than twice our size. So we're 100,000 light years across. There's 220 light years across. And our galaxy has, I got this number, and it blows my mind that it's this divergent, but between 100 and 400 billion stars in our galaxy. You'd think they'd be able to narrow it down a little bit more than that, but anyway, this once again, the sizes here involved are crazy. In the observable universe, the estimates are about 2 trillion galaxies. Once again, just the vastness of space. So let's, as we're wrapping up this podcast, and yeah, it was going to be a short one, obviously, with just me. You're going to not have to deal with some of the inane comments, but let's talk a little bit about interstellar travel. So, I've seen lots of movies about it, lots of sci-fi out there that talks about warp drives and wormholes and things like that. A lot of news recently about warp drives, as there is now a warp drive that is doable according to the laws of physics, right? And that is awesome, amazing news. If you've read any of those articles, besides the headlines, you realize that, well, it is now, according to the laws of physics, something that could be achievable. It's not something that is achievable, at least not with the science that we have right now. Essentially, there needs to be either a lot of negative energy, which is something that we can't do, or a massive amount of gravitational force around a spacecraft, which, once again, we can't do. So while it is physically possible, meaning doable according to the laws of physics, it is, however, not doable practically in any way at this moment, and we have no reason to believe it's going to be doable in the near future. But it is a breakthrough, so let's plaudits to those scientists. But once again, warp drive would take us that distance. The other option for interstellar travel, which obviously I'm sure you've seen, besides a warp drive, would be a wormhole. Wormholes are entirely theoretical at this point, theoretically possible according to Einsteinian rules of physics. Never observed though, so they could exist out there. There would be connections between black holes, is what I understand. However, once again, never observed, and even if they had been observed, it's possible that we could never travel through them or never use them. So, I mean, there's discussions of how they would use an extra dimension to. I said it's beyond the scope of basics in astronomy to discuss how wormholes might work, and given that they're theoretical. Any of the movies you've seen about them are also entirely ideas that don't have any bad grounding in reality. So, so then we're left with just traveling as fast as we can, right? And that increases as science advances. The speed that which we can send ships out, and the speed that they can reach, we're getting better at that. However, we're still dealing with these massive distances. and the furthest object we've ever sent is just outside of the solar system. It's one of the Voyager crafts, which we sent like 60 years ago now. So, and that's just outside of our solar system at this point. Now we can send things faster. However, once again, the interstellar travel is fraught with lots of different variables, lots of different issues, and one of the big ones is that we're talking about travel on a scale that puts mortality into play, right? That we don't the lifespan of a human might not be sufficient to actually even get there, even at the speed, the fastest speed we can send a ship, not using a warp drive. It's possible that an astronaut wouldn't make it there alive. They have to have children on the way, and anyway, there's a lot of things that would be difficult, challenging. Now there's lots of advancements in technology, maybe sort of a light sail that's essentially harnessing the speed of light in order to accelerate an object in space. Once again, these things have grounding in physics, however, not a lot of practical usage as of yet. Lots of advancements in that way, but if we're talking about the reality of interstellar travel, my layman guess here would be that we're not going to see true interstellar travel in the next 100 years. Maybe after that, as we make these advancements in science, maybe in the next 200 years we start seeing some, and then whether or not we can go anything beyond, the closest stars to us depends on the actual feasibility of creating a warp drive and those types of things, because even at with lots of scientific advancement in speed and things like that, the distances, like I said, across the vastness of space here become just truly intractable as far as travel goes, even at large percentages of the speed of light, and so interstellar travel is either you need a moving colony, and there have been in space, and there have been movies about that as well, but in order to send a spaceship out, get there, and if not colonize, be able to come back within a lifetime, even at large percentages of the speed of light, that's almost inconceivable for anything beyond the closest stars. So, a lot of challenges with travel, but a lot of these things are they're the forefront of physics, and if nothing else, they do push our understanding of the universe and our world and our solar system to new depths. So I encourage you to read up on spectroscopy, essentially being able to figure out via light what astronomers can figure out, and what even a layman astronomer is able to help. And turns out that the layman astronomers are doing work out there that needs to be crowdsourced, and so that's something that everyone can contribute to. So if you have just a pretty basic telescope, and you want to find some work that might need to be done, get online and find some interesting things that you can look at and contribute to the field. But as far as basic astronomy goes, I think that'll take us to the end. Like I said, there's a lot more that we could cover, but I should give you some perspective about where we are in the universe, where we are in our galaxy, and a little bit about our solar system. So I hope you enjoy this podcast, and please join us, probably us, meaning me and my co-host, back again for the next episode.